In my earlier video, I explained the concept of threat analysis and the STRIDE threat classification system. In that video, I looked at the theory, but in this video, I'm going to take a look at how it can be used in a real example, using an Internet of Things IoT project. This is going to be simplified, but could help show you how to turn the theory into practice. If you haven't yet seen my earlier video, then you may want to click the link at the top of this video or in the description before watching this video. If you enjoy this video or it provides something useful, then please click the like button at any point in this video, and that will help to share this with others. As a quick recap, STRIDE is a mnemonic that describes possible attack vectors against a system. S is spoofing, T is tampering, R is repudiation, I, information disclosure, D, denial of service, and E is elevation of privilege. You can do the threat modelling yourself, or you can use the Microsoft Threat Modelling tool. There are pros and cons to each approach. One of the advantages of using a threat modelling tool is that it may identify threats you wouldn't otherwise think about. One of the disadvantages is that it's not fully aware of your system, and so may miss some of the important threats. The threat modelling tool is also only available for Windows, and its analysis is not so useful for applications on non-Microsoft platforms. In this case, it's for a Linux running on a Raspberry Pi. For this project, I did use the tool, but I also did some manual analysis as well. Both of these methods picked up some threats that would have been missed by the other. The project I'm doing is for my Raspberry Pi Pixel server project. This is an open source project, and it's available on GitHub, and there'll be a link to my project page in the description. This started life as a non-IoT project. Although it was designed with a web interface, it was only initially designed for use on a secure network, and so didn't include authentication or any of the other security features. I wanted to be able to connect the project to the internet, so I therefore identified this would need to include authentication, and in particular the AAA security framework. So I've performed a significant rewrite of the code to add the login, authentication, and various other aspects. The threat analysis then becomes important to ensure that I'm not exposing this project or other systems to unnecessary risk when it's connected to the internet. Before you start the threat analysis, you should decide on the scope of the analysis. Is this just looking at a particular program or the overall system? If you're restricting the scope, then you may still need to consider the overlap. In this case, I'm concentrating on my own code, but I do also consider the overall system and threats associated between how the code and the operating system are configured. So to perform STRIDE analysis, you normally start with a data flow diagram, such as the one shown here. This identifies where data flows from one system or part of a system to another. You can then look at each of the data flows and apply the 6 attack types and identify the threats and the risks. For this example, I'm going to be performing analysis on the overall design and the application code itself. There are more components. It would also be useful to look in terms of the operating system configuration as well, but I won't be going into that in much detail here. I'll be using 2 different data flow diagrams, and I'll be covering a second one later. This diagram shows the overall design. The main part of the program is a web application written in Python Flask, which is shown on the right here. This uses HTTP, but with login information going to the application, I decided early on that I wanted to use HTTPS encryption. And whilst it is possible to use HTTPS on the web application itself, I decided to use a web proxy instead. I've explained why I made that decision on my other channel, Penguin Tutor. See the link above or in the description. The central circle is labelled as a web server, and this represents the reverse proxy running Nginx, although it's also acting as a web server as well. The unencrypted traffic flows between the proxy and the web application. The reverse proxy could be running on the same computer system, in which case that traffic would not leave the system. But if they are not on the same system, then the network connection between the proxy and the web application does need to be secured. On the left, you can see the human user, and the traffic there is encrypted using TLS. This red line represents the internet boundary, in that traffic going to and from the user will traverse the internet, and this is a significant point for analysis. First, I'm going to look at the HTTP traffic between the proxy and the web application. As I've already identified, this is a potential security vulnerability, as the data is not encrypted when using HTTP. So we already know this is going to identify some vulnerabilities. My mitigation plan is to ensure that this is a protected network. The network protection can be provided by securing the physical network, e.g. using an Ethernet switch, wireless network security, running a secure Wi-Fi network, or avoided completely by installing the web application on the same computer as the proxy. Although, even with these mitigations in place, we may still need to look through some of the threats that are identified. The first threat that the tool identified is replay attacks. This is something I was already aware of. It's protected when going over the internet through the use of HTTPS, and it's basically down to the security of the local network for this. The same for collision attacks. Cross-site scripting is something I've already identified as a possible risk. This is where scripts could be inserted through unsanitized information. I'll mention this in more details a bit later. Weak authentication. Again, I'll cover this in more details later. This is already something I was looking at. And then it also lists elevation using impersonation. Linked to authentication is something I had already considered, both through the authentication, but also considering network-based authentication, which is included as an option. To mitigate against this, then certain configuration criteria is needed, both for the authentication on the application and on the proxy. And then look at the main interaction with the user shown here at this internet boundary. Because of the way this particular app works, then it may be that some of the threats identified here should in fact apply to the web application instead, rather than the web server, which is just proxying the request onto the web application. The traffic over here is over HTTPS, which is encrypted. There's still some threats identified, especially if you look at the interaction with the user at this point. Look at data repudiation. This means about being able to prove what happened. This is achieved through login on both Nginx, which logs URLs visited, and the web application, which logs the user interaction, such as successful logins. Cross-site scripting doesn't really relate to this as it's a proxy. I've already mentioned this for the web application now. Elevation using impersonation. Again, users shouldn't be able to log into the proxy directly, but this is relevant for the actual server that is running the proxy, and in particular the weakness of password logins. I've already created a video on adding two-factor authentication for SSH logins to Linux machines, which is a good way of adding additional protection. The next two threats he identified are both denial of service attacks. A potential process crash. In the case of the web proxy, then it's using Nginx, which is a well-tested application. And to try and mitigate against that problem on the application, that can be done through testing. There are some things that can be covered through configuration. becomes a balance between different security aspects. And I'll discuss that in more details later when I talk about the password hashing. The data flow is much harder to protect against. But one of the things for this is that this is not a critical system. If it's unavailable, there will not be any harm or real risk through a DOS attack. Even if there is a denial of service attack against the proxy, there's a good chance that it's still accessible to get to the web application from the local network without going through the proxy. Remote code execution is not really possible either on the proxy or the web application, and the mitigation to avoid that is just by sanitizing the data received, but it doesn't actually execute any of the data received anyway. So the next one it comes up with is cross-site request forgery. Now this is an interesting one. It's something I forgot to include when I did my manual analysis, although it is something I'm familiar with, so it is something maybe I should have been thinking about. But this is where the tool came in useful. An explanation of cross-site request forgery deserves its own video. I can't really go into the full details of it on here. But I did some research about the Flask module, and there is a module available which adds protection for the login sessions, and I've enabled that in the web application. Another threat it identified was spoofing human user destination. The mitigation in this is looking at the authentication mechanisms, which I'll be explaining later. And finally, the last threat that was identified here is that the human denies receiving the data. It's a repudiation. There's no data that's really passed to the user that's particularly important on here, so it's not something I'm really concerned with. But I have already added login mechanisms, as I've already mentioned, so that would be the repudiation aspect. So as I said, I created a second data flow diagram, and this shows the interaction between the application and the local file system. And there were 7 threats identified by the Microsoft threat analysis tool for this. I'm not going to list them in full. There's just a few that are relevant, so I'm just going to pull these out. And there are 3 that are directly relevant. And the first is about weak credential storage. Usernames and passwords will be stored on a local file system. I'm already planned to use a suitable password hash, and there also needs to be restrictions on who can access that password file. Second was the use of excessive resources. The resources available on the Raspberry Pi are very limited, and it wouldn't take much to overload that. But it's not really a concern. It's not a critical system, but the use of resources has influenced some of my decisions when coding. And the third aspect is weak access control for a resource. Again, thinking about the security of the password file, the risk is also not just being able to access that password file, but that someone with edit permissions to the application source code could also use that for an elevation of privilege. And that's something I've thought about as well. So after performing that initial analysis, the next step is documenting and tracking these threats and providing appropriate resources to eliminate or mitigate the risk. I'm going to show just a few of the things that I've implemented in my project. One thing to remember is that this isn't a one-off task. This is something that can be reviewed at different points in the software lifecycle. So I've already covered some of the ways that I've addressed some of the threats, but there are 4 that I think is useful to cover in more detail as an example of how this threat analysis is then used to make the system more secure. So the ones I'm going to look at are cross-site scripting, weak authentication, weak credential storage, and weak access control for a resource. So these are 4 of the threats that were identified earlier that I just think are going to give a good example of how it's influenced the code that I've created. Looking first at cross-site scripting. This is where an attacker can send data to the server which can then be passed on to other users. Typically this is done by saving some data which includes, say, HTML script tags and some JavaScript code in that. So for example, a regular user, they could update their real name field. So instead of just showing their name, it's got some JavaScript code hidden inside that. And then when an admin views their profile, then that code would be run in the admin's browser, and that could be used to give a user an evaded privilege or create a backdoor username and password or some other way of doing that. The first protection for this is limiting who can edit the user details. And in this case, only administrators can change any of the details. If a user is an admin already, then it doesn't make sense for them to try and deliberately give someone else admin by trying to bypass that. They could just use it using the normal admin means. It may be that I want to give users the ability to update parts of their own profile in future, so this wasn't the only protection I added, so I did look at other ways as well. I've taken a multi-stage approach to sanitizing the data. The first is that Flask itself automatically strips the HTML tags from forms unless it's explicitly told not to do so. But then I've also added additional code in the objects that are updated to check for tags that are not allowed. And this provides a good form of protection, that I'm not only protecting the code as it's implemented at the moment, but I'm also thinking about the future, and some of the additional checks that are currently redundant may be required to reduce this threat in future. Also looking at weak authentication. So what are the authentication methods deployed? I'm going to use 2 here, and the first one is IP address. IP address is something that can be effectively whitelist IP addresses, and they can have a guest-like access. They can access the application without having to log in. This was a decision I made because I wanted to be able to continue to use this with my home automation system without needing to authenticate. If you're using IP-based authentication, then the user or computer can interact with the system, control the LEDs, but only if they're on an approved network. So you can configure that just for a local IP address or your local IP range. And if they want additional access or access out of the network, then they'll need to log in. Then using a standard login via a username and password. I've already created videos on the risk of just using username and password authentication, but it is considered sufficient for this system. If your system is storing critical information, then you may want to look at adding 2-factor authentication or something similar. An important consideration here is that the password should never be stored as plain text. I'll be covering this next. Also, the password should never be transmitted unsecured over a public network. In this case, HTTPS is used between the user and the proxy, and is only ever passed unencrypted over the local network. I've already said about securing that. That's something that needs to have been done. So on weak credential storage, as I've mentioned, the password is only ever stored in a hash form. This means it's possible to check a password is valid by hashing the password that the user provides, but it's not possible to work back to find the original password from the hash. I've covered some of the flaws in this in another video. Essentially, the security of this password is down to the algorithm used. There are different algorithms available, I started by using what's considered to be one of the most secure, which is Argon 2. I implemented that in code, but the problem was that the system would take a long time to process just a simple login. Not only that, if the user tried again, thinking it had not accepted their password, then with multiple requests, this could cause the system to grind to a halt. And this was particularly the case on a Raspberry Pi Zero, which is the lowest spec of the machine that this application is designed to run on. This meant there's a conflict between the level security and the availability. Remember, availability is another of the security requirements in the AAA security framework. Rather than increasing the system requirements, so needing a more powerful processor, I've added a configuration option which allows a security compromise. Use Argon 2 for maximum security, which is useful on a higher specs computer, or SHA-256 for better performance. SHA-256 not as secure, but it works well on the 32-bit operating system and the low spec of the Raspberry Pi. And this brings us on to the file permissions. Restricting access to that file is an important step to ensuring it is as secure as possible. If someone has a login to the system and update access to the password file, they can also grant any user admin access. So it's important to restrict who can do that. Another check that I've included is to check for invalid characters when saving the usernames and passwords. It shouldn't be a problem as only admin can add users, but it does check that nobody is trying to trick the system by adding an extra colon, which could allow you to insert, say, a different password in or other field, which is kind of similar to how an SQL injection attack might be used against a database, but thinking specifically about the file format in this case. And then the fourth one is weak access control for a resource. And I'm going to cover here a bit more than the threat identified by the Microsoft Threat Analysis tool. There's something to be aware of here is that looking at the interaction between the operating system and users of that system. And in most cases, the only users would log on to an operating system for this kind of setup would be administrators, in which case most of this is not really a direct risk. It is still good practice, though, to treat it as though there were multiple users on this system, and that can also help prevent problems in the event that an attacker manages to get on the system, because by setting appropriate file permissions you can prevent either information leakage or that user getting a privilege escalation. It should be fairly obvious you need to restrict who can read the password file. Even though the passwords are stored as a password hash, depending upon the quality of the passwords that the users use, it may be possible to crack those. The next thing to consider is the security of the code. This is something that should be considered for any server, as if someone can edit or change the code, they may be able to add, say, a backdoor. But an additional thing to be aware of in this program is it needs to run with root admin permissions. This is a requirement both to be able to use the port 80, but also to be able to access the neopixels that are the RGB LEDs that it uses. And what this means is that if a regular user is able to edit those executables, they could potentially gain enhanced privileges. There's one idea that could be a potential way of mitigating this, is that you could monitor the executable files. There are some tools available, such as Tripwire, which can be used to alert to changes in the program files. Often these tools will alarm when it's too late, perhaps when the user has already got escalated privileges. But in this example, as long as you're not running Flask in debug mode, the Python code will not be reloaded unless the system, or at least the process, is restarted. So that could be a while after the user's made that change. So using a monitoring tool such as Tripwire could help with catching any malicious code before the system is restarted and before an attacker is able to exploit that. I'm going to finish this here. This hasn't been a complete analysis. It's only covered some of the risks. And I'll put a bit more information on my website, so look in the description for the link to that. The amount of time needed for the threat analysis is going to depend upon how secure you need the system to be. What is in scope, e.g. the operating system versus the application, and the complexity of the program you're developing. I've skipped some of the features and some of the analysis that has been done on this project. But this video has shown some of the steps that needed to be performed and shown this using a real example rather than just a theory. So we sort of started with the data flow diagrams, identified where there's a potential of the data being accessed or being manipulated, and then we looked at how we can apply these 6 threats to that data, and then looked at what changes we could make in the code to mitigate against these. There are some other different models that can be used. STRIDE is just one of them. But whatever method or tools you use, it's helpful to have a framework which helps you to focus on identifying these potential vulnerabilities. And so I hope this video has been useful. If so, please give it a like to help let others know. I'll be creating some other cybersecurity videos in future, so please subscribe if you're interested in future topics. And let me know in the comments if there is anything particular you'd like me to cover in cybersecurity. Thanks for watching, and I hope to see you again in a future video.